factorial that people just were ignoring, and then they were just doing the one. For the standard version of Shellsort, that's how you do the compare exchanges between these two regions. It's equivalent to this. It's just another way of looking at the algorithm. Instead of thinking that we're looking at the ones and just having that sequence of ones that we were doing something with, and then the twos and the threes and the fours, you could think of it as this whole region was being compared against this region, but we just did it using the identity permutation. Now, what I'm going to do instead is do a random matching between those two regions. Do a random matching between these two, a random matching between these two. And do compare exchanges across anything that was paired up with each other. So each of these lines is showing a compare exchange between this region and this region, and the dashed lines are between this one and this one, and then the dotted lines are between the last two. And that would be, those are where we do the compare exchanges now. Instead of doing the identities, we do this random matching.
In which order do you do it?
Doesn't matter.
Doesn't matter?
I mean, it's going to be oblivious, so we're just going to go left to right. Just do them in that order.
Okay, because if you have a circuit, then there is an order.
Yeah, so now we're going to you just fix that as the order. After you've made this random choice, just do them left to right.
Okay, so you do them left to right.
In this order. That's right.
So just once, like a double sort pass?
Actually, I'm going to do it for a constant that's going to come up in the analysis. For the proof, we're going to do it some constant C number of times. Where C is like 6 at most, maybe 3, 4. And then I actually implemented this too, and C equals 1 just works almost all the time anyway. But for the proof, I think I need C equals 4. So we'll do four of these in one pass. Okay? So we'll set C equal to 4. All right, so here's the whole algorithm on one slide. So for the offsets equal to n over 2, n over 4, n over 8, just n over powers of 2. I'm going to assume the n is a power of 2 itself for simplicity. Let AI denote the subarray that goes from I times the offset up to the next value for all the i's. Do a shaker pass. So that's why we have Sean Connery here, this shaker. So just do region compare exchanges between AI and the next, going up. And then region compare exchanges coming down, going back the other way. So a shaker pass at this region level, using, again, these random matchings between the regions. And then do what I call an extended brick pass, where we compare things that are 3 regions apart, then 2 regions apart, then next to each other for even indices, and then next to each other for odd indices, like the bricks. And that's the whole output on one slide. So I think, yeah.
But I'm still not completely clear on region compare exchange. So when I take 2 regions, I match them up in some shuffling way.
Yes?
I compare, and 3 of these items are less than 3 of these, and one of them is bigger.
No.
Do I swap the whole regions, or
No.
Okay.
Just at the, I'm glad you asked that question. So just along the guys who were matched, those 2 guys, we do a region compare between those 2, that's it. So we ask who among you is the minimum, you're going here, who among you is the maximum, you're going there. That's it.
And I do that for all 4 of the things in the regions.
Yeah, just all 4, however they were matched up.
Okay.
And then we do it again and again, we do that C times, that's a region compare exchange.
Got it.
How do you get to random matching?
I just do it, I choose the random matching because that does not depend on the input values. So the algorithm gets to flip coins. That's the model. Allows for the flipping of coins by the algorithm, but those coin flips cannot depend on the input. Because that's still being data oblivious to flip coins. You never depended anything on the input for that. And in these models, the SMC models, there's really simple protocols for Alice and Bob to agree on random bits. They both know are random. That's easy to do too in these privacy-preserving computations. Any other questions about the algorithm? Because this is the whole thing. This is the randomized Shellsort algorithm. Totally oblivious. We didn't make any, other than with the compare exchange at the lowest primitive level as a black box, we didn't make any dependencies on the input values.
So the C is inside there.
Yeah, each of these is a C.
So you do one C between 2 regions. Do it again for that particular region.
Before we go on to the next ones.
But I mean, and before you change I.
Yes. Awesome. That's right.
I mean, that doesn't make sense. But maybe I didn't understand. For the same, it's not for the same permutation.
No, we do a different permutation.
Yeah,
So we
it's
see
different permutations.
independent random permutations
Right.
between the two regions.
Okay, right.
That's right. So hopefully you can see that there's a constant. So this is linear time, linear time, linear, 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 linear. We do this log n times. So total running time is n log n. And the constants are small also. But not 2 to 100. Now for technical reasons with respect to the proof of correctness, since I want this claim that this algorithm sorts with very high probability, what I mean by very high probability is that the probability that it fails to sort will be 1 over a polynomial in n. And for technical reasons, in order to get those kind of high probability claims, as anyone who's read Oblivious book knows, you probably need to stop at some point and deal with small, very small instances that are less than a polylog in size separately. So for the sake of the proof, I actually follow that algorithm on the previous slide with a post-processing phase. In the post-processing phase, what I start with is an array that is polylog near sorted. What I mean by that is that it's almost completely sorted, except that there's a polylog number of elements that might be out of order. They might not be in their proper
When you say
relative.
for the sake of the proof, you mean experiment? I'm not sure what that means.
I have a proof of correctness.
Yes, but
So in
without
order for that
this
to go
step-
through, I'm going to add on this post-processing step.
Right.
I don't think it's needed. And in the experiments I did, I never did this, and it's sorted like.
You mean
all
you
the time.
conjecture that there's a proof that it works without this step?
Yes.
How do you determine that all the polylog elements are in order with Oblivious key?
You can't determine that.
Yeah.
So what I'm saying is I'm going to show that that event occurs with very high probability.
Okay.
And then if that occurs, then this post-processing step is guaranteed to finish off and sort things. Because what we'll do is, on those little, just do one more pass, a shaker pass. But now, instead of using region compare exchange for every region compare, instead we'll just do patch shell sort on that region of size 2 times polylog. That's a deterministic algorithm, runs an n log squared n, but now n is polylog. So that's going to just, the total running time for this whole post-processing step is n times log n squared. So if I can at least get to this point and show that the array is sorted except for a polylog number of elements that might be out of order, then one more thing and you've got it sorted, guaranteed. So this is the real key, is trying to prove this fact. Yeah.
So when you say a polylog number of elements out of order, you mean neighboring elements?
No, they are out of order with respect to where they belong. So if you took those guys out, it would be a sorted sequence.
Okay.
Is that the same question we had over here?
Yeah.
All right. So in order to make that proof, the key component of the proof is in this definition of what I call a leverage splitter. And it goes back to something that's sort of similar to a definition that existed for the AKS sorting network. So in constructing the sorting network that AKS came up with, they used a concept that they called a lambda halver. Lambda halver takes a sequence of 2 n elements, and for any k, will result in a sequence that has the most lambda k of the largest k elements being in the first k positions. So it's sort of a way of getting the approximate separation of large elements and small elements.
You saw them in increasing order.
Yeah, in this case, going in increasing order in all the pictures. That's right. So instead, I define something that's related to that, but not exactly the same. I define something called mu alpha beta leverage splitter. This is an operation that for k less than 1 minus epsilon times n, so there's a slight difference here. Take those largest elements, or the smallest elements symmetrically, return a sequence that has at most the maximum of alpha, some constant factor, times 1 minus epsilon, but now raised to the mu power, where mu is always going to be a number that's bigger than or equal to 1, times n, and then have as a floor the beta. you could have some small number of things that didn't quite